Okay, well, hello and welcome again to our journey into number theory, and we finished last time by talking briefly about Merton's conjecture, and this is based on these partial sums of the Möbius function called capital mu of x. And this function, this capital M of x, I should say, this capital M of x is very mysterious and very complicated, and we don't really completely understand it. As I mentioned, there were various conjectures that were proven to be incorrect, and new conjectures that we don't know the truth about. So in particular, that capital M of x is little o x to the half plus epsilon for all epsilon bigger than naught and x bigger than naught, in the sense that when you divide the two, the limit is 0. Now it turns out this is in fact equivalent to the Riemann hypothesis. So this is a very complicated function indeed, very mysterious function. It's probably, I mentioned before, it's probably false that Stiltje's conjecture that capital M of x is bigger root x. No proof has ever been found for that. Furthermore, it can be shown that the prime number theorem is equivalent to the fact that capital M of x is little o of x. So the Riemann hypothesis, if it's true, will then imply the prime number theorem, but not, of course, conversely. Now the one remaining little bit we haven't dealt with is this, what's going on in the line 1 plus it, so real part of s equals 1. And I've claimed before that there are no zeros on that line, and so that's the next little bit I wanted to finish off, that zeta of 1 plus it is not 0 for any real t. And it all depends on this rather funny looking lemma here, which is really to do with the modulus of various functions of zeta. And this says that for sigma, if the real part of s is bigger than 1, then zeta cubed of sigma times the modulus of zeta of s to the fourth times the modulus of sigma plus 2it is bigger or equal to 1. This is a funny inequality, but it turns out to be very useful in proving that this thing here is not 0. Basically, if we can establish this result, we're going to then assume that if I put sigma to be 1, and we assume that this thing is 0 for some t, then we'll get a contradiction here. So we start off again, as often, with the Euler product for zeta of s. So for the real part of s bigger than 1, we have this lovely Euler representation. We do the usual thing, we're going to take logarithms of this, and that will turn the product into a sum. And then the minuses, we get a minus out the front here. And we can then expand this log using the Euler series, and we can write the log then as this infinite sum here, which we've done before. And we're going to now equate the real parts. Now, of course, the logarithm of a complex number, you take log of the modulus plus I times the principal argument. And so the real part's going to be log of the modulus of this, and then we can take get the real part of the inside here. We can peel off the p to the minus ks, and then we want the modulus of p to the minus it, and we can get that by just doing some calculations, and you get the cos of kt log p. Standard complex analysis calculation. Now it's very easy to show. Here's a nice little trig identity. You want to brush up your high school trig, you can prove this one. It comes out fairly easily. It's very easy to show that 3 plus 4 cos phi plus cos 2 phi is twice 1 plus cos phi all squared, and hence this quantity is non-negative. So if I replace phi now, keeping my eye on this, replace phi with kt log p, multiplied by this term here, and then sum, we can then take this identity here, and which we now know is positive, and we can write it like this, and we can then write this back in terms of the zeta function. So we can take these terms inside and write it back in terms of the zeta function. So you'll get the modulus of zeta of sigma plus it from this term, and you'll get the modulus of sigma plus 2it from this term, or the logarithms of them. So we can rework backwards what we did above and get this inequality. Finally, if we exponentiate both sides, then e to the naught's 1, and so that means, and I can pull all these together then, which simply turns into this, and that means that's bigger than 1. So that's how the lemma works. Now we need to use the lemma then to prove that zeta of 1 plus it is not 0 for all real t. Of course, when t is 0, we've got a simple pole there, this becomes infinite. So all we do is I take this previous lemma here that we just proved, here it is up here, that's what we just established, and I'm going to divide both sides by sigma minus 1. Except the sigma minus 1 on the left hand side I'm going to write as sigma minus 1 cubed over sigma minus 1 to the 4th. Now, and this is valid for sigma bigger than 1. What we're now going to do is let sigma go to 1 from above. Now if t is 0, then sigma of s goes to infinity as s goes to 1 from above, and that simply says infinity is bigger than infinity. Well, that's not very useful, so we're going to assume that t is not 0. Now, looking back, try and fit both of these in the picture here. Looking back at what we've got here, the zeta has a simple pole with residue 1 at s equals 1. So that means this first factor there, so we're multiplying zeta of s by s minus 1, and that'll clear out the simple pole, and we'll just get the residue as s goes to 1, and that's 1. So that first factor is tending to 1 as s goes to 1. Now if you look at the third factor, this tends to zeta of 1 plus 2t, which is finite, because the only pole that zeta has is at s equals 1, and t is not 0 here. Now if, big if here, if this does have a 0 for some t, then we can rewrite this middle term here. We can just subtract off 0. Because if this is 0, then we can subtract off nothing doesn't do any damage, and then as we take a limit as sigma goes to 1 from above, this is just the derivative of zeta of 1 plus it, and this thing is bounded. Now we'll have a look at that's why this is, but at the moment let's just assume that this is in fact bounded. We've probably got enough machinery to see that already. So that would then say that as sigma goes to 1 from above, that's going to 1, that's bounded, this is bounded, assuming that zeta of 1 plus it is never 0, but of course this is not bounded, this is going off to infinity, and so we get a contradiction. And that was all predicated on the fact that this was 0, and therefore we've shown that it cannot be. Now I'm going to introduce a technical tool, and I'm going to state without proof some various bounds on zeta and its derivative which we'll need for the prime number theorem. Now the technical result is this fairly important Euler summation formula, which, as you can gather, goes back to Euler, and again it's just another way of writing a sum using integrals. Writing a sum using integrals. And it says that you want f to have a continuous derivative on the integral naught capital N, where n is a positive integer. Then the sum, n equals 1 to capital N of f of n, can be written as the integral of this f from naught to capital N, plus we get some term on the end here, some sort of remainder term. So it's very nice, it connects the sum back to the integral via this rather strange looking final term, which is the integral of this in here, of course, is just t minus the fractional part, the integer part, the floor of it. So this is the fractional part of t times f dashed of t. Now, just to give a quick proof as to how this works, we begin by looking at this term, the floor of t times f dashed of t, and so there it is. And you can pull that, you can turn the floor of t into just n minus 1, because t is on the integral between n minus 1 and n, so its floor is going to be n minus 1 on that interval. And the point is now you can actually integrate this and get this expression, just a straight integration. And I can split up, I can take one of these minus fn term, I can take out, and I'm left with this particular expression here. You can see why I'm going to do that, because when I sum, this is going to give me telescoping series in here. So that's what I do next. I sum from little n as 1 up to capital N, and so this term of the floor of t, f dashed of t, is just this sum. Plug in what we just derived. This is a telescoping series, so you allow it to telescope, and all that survives is capital N f of n minus this sum. So I can rearrange this now and write the sum that we want is equal to capital N f of n minus this sum here. Now we look at that other term that we had above, which was the t times f dashed. And again, you can integrate this one by parts. Use integration by parts gives you this minus this. And then I can just get rid of this term here from in here. So I can replace that with this plus this. Combine the two integrals together, and we end up getting back to the integral that sum that we just had. That is, we end up with something like this. Here I'm taking limits, but so just to go back, we end up then with this sum. We combine those two terms together, and we end up with this Euler summation formula. Now we can, assuming the necessary integrals and series converge, we can change variables and limits to obtain this formula for the sum from capital M up 1 to infinity. We just do what we had above there, and hence we can apply this now to the zeta function. And so I'm going to take the first capital N terms of the zeta function, plus there's the tail. And I can apply the Euler summation formula just to the tail part. So we keep the sum from n equals 1 to capital N, and then we use Euler summation on the tail, and we just substitute in and gives us this expression. This integral we can easily do. That's it. You can leave you to check the details of that one. And here we have our term here. Now this formula actually turns out to be very useful. By the way, if you put capital N as 1 into here, then you get the expression that we had before. This one just turns into 1. This turns into 1 over s minus 1, and we have this integral here. And we've seen this expression before for zeta of s. And so this is really just a generalization of the formula that we had before for zeta of s in terms of this fractional part. Now I'm going to state without proof a couple of important bounds on the size of zeta and its derivatives. So if sigma is bigger or equal to 1, t bigger or equal to 2, then we get a bound on the modulus of zeta of sigma plus it. Turns out to be less than log t plus 4. In other words, it's just less than a constant times log t. We can also get a nice bound on the derivative. The modulus of the derivative is less than a half log t plus 3 all squared, i.e. it's less or equal to some constant times log t all squared. Now the proofs of these are just basically applying the Euler summation formula and doing a bit of fiddling around and estimations and things. You can find proofs of these in Apostol's book and also in Jamison's book, so I thought I might skip through those. Let me just state again without proof another important result that we'll need for the proof of the prime number theorem, and that is 1 over the modulus of zeta is less than some constant times log of t to the 7th. And the logarithmic derivative, the modulus of the logarithmic derivative, zeta dashed on zeta, is less than some constant times log of t to the 9th, whenever sigma is bigger than 1 and t needs to be bigger than e or equal to e. Now, the reason we're interested in this is because one of the proofs of the prime number theorem uses the logarithmic derivative, and so we need to get some control on the size of the modulus of the logarithmic derivative. Now again, the proofs of these are very long and quite technical, so you can see Apostol's book on analytic number theory or Jamison's book on the prime number theorem. As I mentioned, this logarithmic derivative is going to play an important role in the proof of the prime number theorem. Well, I wanted just to, we know that the zeta function has a simple pole at s equals 1, and we know the residue is 1. So I want to look at the various Laurent series now for zeta of s and 1 over zeta of s and the logarithmic derivative of zeta of s to have a look at, just to eke out a little bit more of what the Laurent series looks like. So at the moment it looks like this. You've got a simple pole at s equals 1, so that's the principal part, and the residue is 1, and then you'll get other term, the Taylor part of the series. Well, it'd be nice to know what this A0 is. What's the constant term in the expansion for zeta, the Laurent series for zeta? It turns out to be worth knowing because it's very pretty, as we'll see. And I just remind you about this this limit here. If you take the sum r as 1 to capital N 1 over r minus log n, then as n goes to infinity, this approaches Euler's number gamma, which you will have seen in any basic calculus course, that although this sum diverges, if you subtract off log n and then take a limit, the limit exists, and in fact it is this number gamma. Now, the first thing I want to observe is that this number gamma can be written, here's a nice representation for gamma, it can be written as 1 minus integral 1 to infinity of the fractional part of t on t squared dt. And just as a quick proof of that, the existence of this limit is well known. You would have seen that in basic courses on calculus, and I'm going to apply the Euler summation formula with f of t is 1 over t. So the Euler summation formula we had before, I can now take this sum from 2 to n, which is just this integral minus this other integral here. This one we can evaluate easily, and I need to add in the term n equals 1, so I've got to put an extra 1 on the other side, and I'm left with this here. Well, there we have it, because I can take this on the other side, we get the minus log n, let capital N go to infinity, this goes to gamma, and so gamma is equal to this expression. Okay, so that's easy to see. Now, for our lovely result here, we can now see that the zeta of s minus its principal part goes to gamma as s goes to 1. That is, the Laurent series of zeta of s just looks like, well, there's our simple pole at 1, residue 1, and the constant term turns out to be gamma. Plus, we're going to get some more terms, these c sub n's. These numbers are called the Stieltjes constants, and it can be shown using the Cauchy integral formula. It's not a hard exercise to show using Cauchy integral formula that these Cn's are given by this expression. So these are interesting constants in their own right, the so-called Stieltjes constants. Now, this follows immediately from what we did above, that formula that we had back above theorem 5.5. If we simply take a limit as n goes to infinity back there, we end up with this, and that was equal to gamma. So I'll leave you to finish that bit off there. Finally, the little corollary to this, we'd like to know what what is the Laurent series of 1 over zeta of s and the logarithmic derivative look like? Well, 1 over zeta of s, in fact, is analytic, and it's simply, so we're on some punctured disk, centre s equals 1, then that's the Taylor series of 1 over zeta. So the constant term, of course, is 0, because as you go to 1, this becomes 0, and then you simply get 0 here. So the constant term is 0, and the coefficients are 1, and then you get a minus gamma turns up again here in the Taylor series. The logarithmic derivative, this has a simple pole, of course, at s equals 1, as you can see. The residue here is minus 1, and the constant term is gamma, plus the rest. And I'll quickly take you through a little proof of that. And this is just a nice exercise in complex analysis, really, and playing with Laurent series, which are always fun to do. Now, we've already seen that zeta of s looks like this. We've shown that the constant term is gamma. And I'm going to factor out 1 on s minus 1, so I get 1 plus gamma s minus 1 plus big O s minus 1 squared. Equals 1 on s minus 1 times, I'm going to call what's left g of s. Now this g of s then is analytic, and g of 1 is not 0. G of 1 is not 0 because I'm multiplying zeta of s by s minus 1, and we know that that will get rid of the singularity. So, when I take 1 over zeta of s, then I just turn this upside down, I get s minus 1 on g of s, and that's analytic at s is 1. So if I give this beast here a name, I'm going to call that f of s, and because this is analytic at s is 1, f has a Taylor series about s is 1, so we can write down the Taylor series will have that shape. So I've got a constant a1 s minus 1, a2 s minus 1 squared plus terms of order s minus 1 cubed, and the product of these two is 1. So we can then simply replace zeta of s by its first terms of by its Laurent series. We can replace f of s by its Taylor series, and the product of these has to be 1. And then we just take a deep breath and expand, and we see what happens. Well, you can see from here you'll get an a naught on 1 on s minus 1, and you can't have a 1 on s minus 1 term because this has to be equal to 1 for all s, and so that means the a naught must be 0 to clear off that product there. If we compare the constant terms now, the constant terms are going to come from well, gamma times a naught, but a naught is 0. And then we're going to get that one multiplied by this one, and that's the only constant term, and the constant term on the other side is 1, so a1 is 1. Now I look at the coefficient of s minus 1. So the s minus 1 coefficient is going to come from here. I get a1 gamma, and the other s minus 1 is going to come from the a2, and so that means my only constant term I'm going to get is a2 plus a1 gamma 0, and we've just shown that a1 is 1, and so that means a2 is minus gamma. So plugging that in, I get 1 over zeta of s then is s minus is 0 plus 1 times s minus 1 minus gamma times s minus 1 squared, and so on. So there's the Taylor series for 1 over zeta. And for the logarithmic derivative, I again go back to this g that I defined before, and so zeta of s is g of s on s minus 1 as above. Take the logarithm of both sides using the log laws. We differentiate both sides, so I get the logarithmic derivative there, and this is minus 1 on s minus 1. So that one I can copy down. This one is analytic, so this has a Taylor series. So I can just write that down as the Taylor series of g dashed on g, because g of 1 is not 0. So this is what and this g is analytic at 1, so this has got a Taylor series. Now I can write zeta dashed as zeta times zeta dashed on zeta, and then I can just plug in what we know. So zeta of s, we've already seen, that's the Taylor series, sorry, the Laurent series of zeta, and we've seen that zeta dashed on zeta looks like this from up here, and again we can just take the brackets out. So to expand out, we get minus 1 on s minus 1 squared, we get a naught minus gamma on s minus 1 plus big O of 1. So that's an expression now for zeta dashed, but I can differentiate zeta and get zeta dashed. So differentiating the series we already had for zeta, we get this term plus terms of order 1. And if you compare and contrast, well, they match nicely. There's nothing for this to match with, so that means the a naught equals gamma. So finally then, we have the logarithmic derivative has this as its Laurent series, minus 1 on s minus 1 plus gamma plus a1 s minus 1, and so on. Now in the next and final section of this chapter, we're going to have a look at the Bernoulli numbers and see how they also connect in with the Riemann zeta function.